Hello, my name is Brandon Heavener. The problem chosen is problem 14 from chapter 9. It states water falls without splashing at a rate of 0.250 liters per second from a height of 2.60 meters into a 0.75 kilogram bucket on a scale. If the bucket is originally empty, what does the scale read 3 seconds after the water starts to accumulate in it? So what we're working on, you initially have a bucket similar to this one here that is empty, sitting on a scale. Then, 3 seconds after, you have a bucket with water accumulated into it. Now, what we're trying to find is the force needed to stop that very next droplet of water once that after 3 seconds of accumulation has gone through. So at 3 seconds, you have 3 seconds at a rate the water falls into it at 0.25 liters per second. So after 3 seconds, you have 0.75 liters of water in the bucket. Now, the mass of the water of 0.75 liters, as you can see through cross multiplication, you come out to get 0.75 kilograms is equivalent to that amount of water. Now, what you're trying to work out is to find when your water initially starts from a point at a height of 0.26 meters and falls down to the height of 0, which is the top of the water in the bucket that is sitting on the scale. You're initially trying to find the force needed to stop that droplet of water. Now, with your energy equation, the work in this experiment, there's no work. So what you're left with is your initial energy and your final energy, with your initial energy being mass times gravity times height, and your final energy of 1/2 mv squared, which m being mass and v equaling to the velocity. Now, if you work this out, the masses cancel out. You're left with 2gh equals v squared. So your velocity is equivalent to the square root of 2gh. Now, moving on, you have an initial momentum equivalent to the difference of mass times velocity, and your final momentum equaling to 0. So your change in momentum is equal to the negative difference in your mass times velocity. But the force equals the change in momentum over the change in time, which is equivalent to the negative change in mass times velocity over the change in time. Now, so your force is actually equivalent to the change in mass over change in time times velocity, where your change in mass over time is the rate at which the water falls through the mass. So that equals out to being 0.25 kilograms per second. Now, you're going back, your velocity, remember, is equal to the square root of 2gh. Now, the net force required to support the bucket is equal to the mass times gravity plus the difference of your mass over the difference in time times the square root of 2gh. Now, checking your units, Mass is in kilograms. The acceleration due to gravity is mass over time squared. The difference in your mass over difference in times is kilograms per second. And the square root of 2gh equals out to being mass, or meters per second. So that equals out to being, giving you your final net force in newtons, which is equal to the kilograms meters per second squared. Now, remember, mg is equal to the mass already in the bucket to begin with after your 3 seconds. So, mg is really the mass of the water plus the mass of the bucket times gravity, which the mass of the water is 0.75 kilograms, plus the mass of the bucket, which is also 0.75 kilograms, times gravity. So that equals out to being 1.5 kilograms for the mass of the water and the bucket added together, plus the acceleration due to gravity, which is 9.8 meters per second, which equals out to being 14.7 kilograms meters per second squared. Now, going back to our force equation, when you plug in the numbers, going back, you still have 1.5 kilograms times 9.8 meters per second, plus the rate that the water falls into the bucket, which is 0.25 kilograms per second, times your velocity, which is the square root of 2 times 9.8 meters per second, times the height, which is 2.60 meters. Working that out, you end up getting 14.7 kilograms meters per second plus 0.25 kilograms per second times 7.138627 meters per second. Moving down, you're left with 14.7 kilograms meters per second plus 1.7846 kilograms meters per second squared. When you add those together, you're left with 16.5 kilograms meters per second, or 16.5 newtons, which is the force required to stop the water, that last drop of water in your bucket. All right, thank you.